So today we will start to talk about the von Neumann theory for quantum ensemble. So from the quantum mechanics, you just use it before the eigenvalue, the energy levels, and by energy level you try to find the partition function or canonical ensemble or something like that. But this is this subject is completely different. So we will work on the operators. Mainly we will introduce the operator for the density function rho, and we will study a quantum version of Liouville theorem for this quantum ensemble. So actually we will study the dynamics of this quantum operator when you have the Hamiltonian for the system. So when the Hamiltonian of the system is fixed as a quantum operator. And we will do all them in the Heisenberg picture, when we will freeze the state of the system and give the time evolution to the operators. There is a two approach to quantum mechanics. You know, one is the Schrödinger approach. So in Schrödinger approach, you will study the evolutions of the wave function of the system. So the other one is the Heisenberg picture, when you study the time evolution of the operators. So in von Neumann theory, mainly we will use the Heisenberg pictures. And you will learn here that if you find the operator rho, you have a two possibility to represent the operators. You can represent the operator in the coordinate representation. This is the plan of this chapter. Actually, it will take maybe 2-3 lectures to finish all of them. Coordinate representation, where we will be interesting to define the matrix element of the operator of the rho when it's sandwiched between the R and R star. So this is, we call it rho R prime. So this is the representation of the operator in the coordinate representation, and sometimes it's useful to do the matrix element, find the matrix element in the momentum representations. This is another possibility. And the other one is that discrete representation. So discrete representation. When you have this Hamiltonian, when you have the eigenvalue of the Hamiltonian as a discrete spectrum over some real numbers. So in this case, we have looking for the density operators between the two discrete state n, which is corresponding to energy level En, and this is corresponding to energy level Em. And this operator is given by this element. If you give me the matrix of the rho, so I can find for you all the quantity which we studied before in ensemble theory, like expectation value, like everything. So mainly the quantum theory is used to take the expectation value of the statistical quantum operators like that. So And you needed to know that these two representation of the operator rho, which we call it these density operators, can be related to each other. For example, you needed to know that from the quantum mechanics that we will see that. If you wanted to find, for example, this, and you don't know exactly the form of the state n and m, they are the elements of the Hilbert space. They make a focus space over the spectrum of the energy of the as a real numbers. So to take that, you can use it a coordinate representation like that. If you be a little bit lucky, so you can rewrite this expression in terms of the projection of the state over the R. You know, this is it looks like that. For example, this is just a picture. If you take this as a R and this is your vector state in the Hilbert space, so if you make it a projection, so n over R gives you the projection of the state n over R or R over n or something different. So what we call it Rn is actually, this is we call it psi nr, the eigenvalue of the Schrodinger equation. But this is the representation, we will use the Dirac notation. So instead of the psi nr as the eigenvalue of Hamiltonian, we will use the notation of the Dirac. And you know that they are normally, they are eigenvalue of some type of the Hamiltonian here like that. So this one line has a very rich structure actually. It shows that you can relate the matrix representation of any operator to the integral representation from discontinuous to the continuous one. This is your first touch with the modern quantum mechanics. It's the first touch. The second touch will be very painful. You needed to learn what is the quantum field theory. And the third attack, it will be very dangerous for you. I don't know you can be survived from that or no. But this is the first experience about the real writing of the quantum mechanics. Look at that. So, I told you this is a very interesting. You know, we started just with basic concept. So, if you think that as an operator, any operators, so the matrix element can be represented as a double integral over the eigenvalue of the Hamiltonian and the function which is defined over the coordinate space. So in one side you have the matrix element of the operator. In the other side you don't have any matrix, you have a continuous functions. This is a continuous function of this same operator in another space actually. And to relate them together, so you needed to make the integral over the region of the space, a double region of space, a two-dimensional. One integral that runs over the dr prime, and one integral runs from the dr. So something's non-local. This is a non-local because to calculate that, you don't need it only rho. You need the value of the rho near to this also. What is the integral? Integral means that. Integral means that to find the average, for example, you need to consider many quantities And to take the integral, you don't need it exactly what is that. You need also all the points near to that in some region of the space. Non-local quantity will be related to some local matrix elements. In this chapter, we will think about the rho as a quantum operator responsible for the density. This is exactly the same as the concept of the probability of the finding a system with the given energy at the same temperature. The Boltzmann equation, exponential minus beta. How you interpreted that equation? The interpretation of this equation minus beta En, sigma E minus beta En. It was the probability of defining the system at the energy level En when the temperature is fixed at the beta. We will introduce a quantum version of this operator. The quantum version of this operator will be rho, P. Instead of the P, we will use the operator rho, and instead of the E, you will see that the Hamiltonian is responsible for that. And instead of the sigma, we use a concept called a trace of the operator. In this case, you can translate the classical probability theory in statistical mechanics to the quantum. And this is, of course, more general than the classical one. And whatever you did it here, like expectation value and these things, you can do that. Instead of the sigma, you can do that by the trace. So from this first whiteboard, you understand that what you needed what we call it in mathematical physics as a representation theory. Representation theory is how to write an operator different forms, like matrix, like that, how you can relate them to it. So, any question about here, because I need to remove it.
Doctor? What do you mean by a trace?
I will explain that. I expected that you know what's the trace of the matrix or operator in the past, but anyway, we will start and I will explain you what's the trace. Trace is the summation of the diagonal elements of this matrix, which is connected. So you have a rho 1, 1, rho 2, 2, rho 3, 3. So the trace of any matrix element will be sigma n, rho, and n. But not very easy to calculate this trace. Sometimes you needed to take the trace in the coordinate transformation. Sometimes you need to do it in the momentum representation, and sometimes. I needed to remind you the Heisenberg picture in quantum mechanics. This chapter will start by writing the Heisenberg equation of motion for the operators in quantum mechanics. So you needed to know that what that means. So I started by the foundation of quantum mechanics. So what you needed to read is that, not in my lecture, you needed to understand this lecture because of the quantum mechanics. You can go to the Walter Greiner, the quantum mechanics book. Chapter 5 is a representation theory. Citation theory. Foundation of the mathematical foundation of the name of chapter is Mathematical Foundations of Quantum Mechanics. So this is a very modern textbook for the bachelor level quantum mechanics. That was a textbook which I read it in the bachelor level. So, Springer. I think you have the ebook, no? You have the, so you can distribute too. So, this book, just one chapter, if you want to go in the deep, you needed to read this chapter, otherwise my information will be just introduction to that. So, this Walter Groening is a series of the books started from the classical mechanics to the advanced topics like nuclear physics, because he was the nuclear physicist. So he has a very, very good book about the nuclear physics theory. And also a lot of information about the experiments inside the books. Anyway, I will start by the Heisenberg Heisenberg representation of the operator in quantum physics. So, in Heisenberg pictures, portrait of quantum mechanics, you consider each operator as a function of the time. You have to relate this operator at the function of the time to its value at the time is 0. So you needed to, if this is a time is 0, and you have the operator at the time is 0, so the first question in classical mechanics or any other dynamical theory is that when t is passed, what's the form of the operator? In Heisenberg picture, we define the operator in the following form. We define that. We define this. This is a representation of operator at any time. If you give me the operator at the time is 0, sometimes they call it this Schrödinger operator, because in Schrödinger picture, you don't talk about the time-dependent operators, you talk about the evolution of the wave function. If you give me the value of the operator at time is 0, and if you give me the Hamiltonian, and this Hamiltonian should be Hermitian, no? Hermitian. What does it mean, the Hermitian operator, you know, this? How I know that? For example, I give you this operator.
Do the conjugate and the transpose.
Okay, I will. Okay, let's wait. I give you this operator. Is it Hermitian? But it's kind of complex. Where is the I? There is no I here. How I know this is a kind of Hamiltonian? Can I take this as a Hamiltonian or no? Or this operator, for example. This operator. Very easy operator, just x, not y. No. Is it this Hermitian? Is it this Hermitian? Can one person came to you and say that take this as your Hamiltonian? How you know that this can be Hamiltonian or not? You needed to check what is the Hermitian. Huh? How you know that operator is Hermitian or not? How you know? How you check that?
You can move it from side to side without effect.
Yes, something like that, but we need to make it very clarified. For example, this operator is not Hermitian, but if I just replace the I here, it will be Hermitian. Not because of the I, because of what your classmates say, but we need to make it more technical. To say that it's in the bracket, because this is not our main target. If you want to know an operator is Hermitian or not, you needed to check one thing. Take two function, any function, and put the operator here. And just check that, is it possible to Yes. What your referent say that is that if you want, it looks like it should be passed from here and sit with that and take the thing, and that this is doesn't change for that, nothing for the first. It should be. It can pass from that and sit it here. But if I give you this as a definition of Hermitian, take phi and say two function, any function. You don't need to specify the function. Don't put x or x squared or sin. This is an arbitrary function. For example, by that, you can show that the operator R is minus I h bar partial x is Hermitian, because you can do that, these calculations. And here you normally need to use the part by part integration. No? You will have a